So I'm really looking forward to this session using the probability of success with our guest rockstar Graham Banks, who's the founder of Rich Reserves and the principal geologist of Southern Geoscience Consultants. So Graham will be showing us a holistic exploration workflow for critical metals. So thank you so much, Graham. I'm really excited to hear from you. So yeah, thank you for joining us.
So thank you everybody for joining in either your morning or in your evening. Bit of background, as Jess said, I'm the founder and principal geologist of an exploration consultancy called Rare Earth Reserves, based now in Vancouver, and I can assist their clients with structural geology, exploration strategy, license block evaluations, or in the mineral system framework for copper, cobalt, gold, rare earth elements, petroleum, etc. I'm also a principal geologist associate for Southern Geoscience Consultants. That's a team with global experience of acquisition and processing and interpretation of exploration data, headquartered in Perth and now expanding in North America. I'm going to present a workflow to aid decision quality for metals exploration, and it stems from all my experience that I just mentioned, and also numerous business development opportunity reviews. And I've applied what I'm going to talk to you about, from screening countries all the way down to just core log drilling. So I approach mineral exploration not just as a geologist, but obviously from the point of project efficiency, the uncertainties, trying to preserve a project's value for that 20 years from staking ground to it becoming a mine, and obviously geological risk analysis, as we all should be doing. The workflow I'm going to summarize is built around trying to predict where a mineral system at regional scale will have deposited mineral deposits during those short moments of dramatic crustal deformation. If some of these bits are unfamiliar, rest assured that this is a globally standard practice exploration workflow, has been for 3 decades. And all I've done is adapted it from sediment-hosted petroleum exploration to igneous-hosted rare earth element exploration. Some copper companies and diamond companies also use this workflow, which means it can be applicable for copper, gold, lithium, graphite, etc. exploration programs. Because fundamentally the exploration business is the same regardless of the commodity. We're trying to discover undiscovered profit somewhere underground before another company does that. This is also just a 35-minute version of a 2-day-long professional development course that I can tell you about a little bit later as well. So I am going to share my screen. All right, here we go. So holistic exploration workflow for critical metals from the viewpoints of efficiency, uncertainty, value, and risk. So we're going to go through 3 themes: the value of acquiring new information and its impact on a prospect's chance of success, why build a geological success case model, and then a mineral system approach to build a riskable portfolio of opportunities through province, then district, then play, and then prospect scales. We want to do this because we want the geoscientists and the strategists and the policymakers and the investors all to be more closely aligned. We're using a global, systematic, repeatable workflow that helps us to only collect data that improves the team's chance of success for its prospects, so that we can compare and then rate and then prioritize our portfolio of opportunities across different commodities. That's what our investors are trying to see in our geoscience work. Let's all get up to on the same hymn sheet from definitions. First of all, risk is the quantified probability that an event will indeed result in a specified loss or failure. Uncertainty is the limited knowledge that prevents us from giving an exact description either of the current state or a future outcome. And so we always present as a range of possible outcomes. Value is the maximum amount of money that an economic agent is willing to spend to take a stake in your project, rather than spend it somewhere else, like on cryptocurrency or cannabis stocks, for example. Mineralized play is a group of genetically related mineral occurrences within a chronological unit. Chance of success is the likelihood, as a percentage, that the geological chance factors that must all coincide to form a mineral deposit did indeed do so. Chance of success is 1 minus risk. So first of all, mineral exploration challenges. It's an economic activity. We need to help our investors to get an acceptable return on their capital. And if this statistic is anywhere near correct, that only 1,000 prospects are required to find one new mine, that's an unacceptable rate of return. And the research from David Groves and Santosh in 2015 showed the minerals industry as a whole delivered a close to zero return, which is why people buy cryptocurrency instead. The solutions are simple and easy to understand, and we've known about them for a long time. We need to reduce uncertainty and risks in our projects, increase their efficiency, their chance of success, and therefore investor and executive management's confidence in our geoscience work. So to be efficient, we can basically, as a summary, we need to move from descriptive to predictive targeting, starting at a regional scale, that enables us to compare and risk and rank assets and preserve a project's value through that long term between staking ground to it becoming a profitable mine. So theme 1, the value of acquiring new information and its impact on a prospect's chance of success. Here is traditional deposit scale exploration. First of all, nature either did or did not deposit a large mass of rare earth elements under here 100 million years ago. And then by a complete fluke 100 million years later, geologists who know a little bit about rare earth element mineralization walk past on their Sunday afternoon stroll and see these mineralizations. Investigating them is a bit like evaluating 2 dice as a very simple example, and then trying to make a return on our investment. So if you can imagine that a 1 and a 1 on 2 dice, which were rolled 100 million years ago and then placed under cover, is a mineral resource, and any other number combination is no mineral resource. Before those geologists start to spend any money, their prior chance of success is 1 in 6 multiplied by 1 in 6, which is a 3% chance of success. Another way of saying that is a 97% chance of failure. We're not trying to be negative, we're geoscientists and we're optimistic, but we always want to make sure that our prospect sits between the success case and the failure case scenario, and where we know where that is on the scale. The chance that an alkali igneous rock yields a rare earth element mine is going to be a much lower chance of success because there are more than 2 independent variables that must coincide. The geoscientists form a company, they go to the capital markets, they raise $1 million of investment. 1 million divided by 36 gives a game value of only $28,000. That's all the project's worth. So with their first $500,000, what information are they going to collect to improve their estimated chance of success? What type of geological data, or geoscience data, sorry, is going to have the biggest impacts on the project's value, uncertainties, and risk? Should they acquire airborne gravity or helicopter-borne radiometrics? Should they employ lots of summer students to go out into the field and collect soil and sediment samples to analyze? And collecting that new information and analyzing it and interpreting it is a bit like seeing a little bit undercover. It's like taking a peek underneath one of those cups. And after having done all that work, the estimated chance of success may improve. But as you can see here, with a number 6 on the dice, 5 of 6 outcomes reveal that we can't win. Most outcomes in this scenario show that the new information tells us to stop the project and preserve the remaining value of the organization. And if once that cover was removed, there was a 1 on the die, then maybe the project should continue, but still maybe it shouldn't. Because the geoscientists need to think which of the new data sets caused that 1. And as you can see from the equation at the bottom, the chance of success hasn't changed. It's still 1 in 36. So the geoscientists think, well, what other types of information should we collect now with our remaining $500,000 to try and improve the chance of success and the game value again? Should they conduct trenching? Should they do lots of lab analysis of all those rock samples that were collected by the summer students, laser ablation, SEM, XRF, etc.? Or should they just do some exploratory drilling? The new information is analyzed. It's a bit like taking a peek under the second cup, looking under cover. What's the new chance of success? Damn it. What we see here is we see a 6 and a 1. There's no mineral resource here. And despite the exploration company spending $1 million, the chance of success didn't change, and neither did the geological value of the project. the geoscientists need to think to themselves, well, what would have increased the estimated chance of success? What were rolled on the dice 100 million years ago and then covered up until now? Bigger question, do traditional exploration methods add value or just cost? Because, for example, airborne gravity doesn't reduce exploration risk. There isn't a concept called risk underground that can be detected. Aha, there it is. Doesn't indicate rare earth element deposits directly in carbonatites either, and neither do drones or machine learning or portable XRFs. These are all very specific tools to collect and understand very specific data types. But what we need to be doing to reassure our investors is move towards probability of success, uncertainty, risk, and impact, and put those on maps so that we can then move an organization to enhance its decisions. An even bigger question, why do we spend exploration dollars collecting new information if it doesn't add value or reduce or increase the chance of success? And the reason that we collect new information is because we want to make our success case geological model more robust. We want to narrow the uncertainty ranges in each of the input parameters and then help us also to try and estimate a range of possible commodity tonnage sizes under the ground. The value of information lies in our ability to make better decisions, i.e. drill prospects in profitable underexplored regions and save the drilling costs by not drilling in unprofitable or overexplored regions, which increases the drilling efficiency of the entire sector and hopefully increases the sector's success rates. It's not as simple as just two dice. If an exploration project needs 3 independent variables all to coincide, like trying to get 3 ones on the dice with multiple outcomes for each dice, then we get very quickly to a 1 in 200 chance of success. If there are 4 independent variables, we're now at 1,300 chance of success, which tells us that as we build our prospects, we make sure that they adhere to the laws of thermodynamics and fluid dynamics, brittle failure. We should also be making sure that every prospect adheres to the laws of probability, which takes us very nicely to this slide, where Rio Tinto have said that only 1 in 1,000 mineral targets becomes a profitable mine. Only 10% of gold deposits have enough gold to justify further expenditure on them, for example. We really need to be able to improve our chance of success in our industry. So that moves us to the second theme, why build a success case geological model? As we've just seen from the simple dice analogy, exploration is a high stakes game of risk with a low chance of success. So we think about a prospect's chance of success. What does that actually mean? It's the exploration team's confidence that their success case geological model is an accurate depiction of what's happened in nature over hundreds of millions of years. So every prospect needs to have its success case parameters to be predicted, ideally before an expensive drilling campaign. Here's an example of a predictive success case statement for Rare Earth Element deposit project that I worked on. The team hypothesized that in the Paleozoic era, there was subduction, and the mantle was enriched in rare earth elements, so a rich source of commodity. Mantle melting then occurred and mobilized between 20 and 100 million tons of rare earth elements during continental collision 15 million years ago. Magma has ascended up a strike-slip fault and coalesced as carbonatite dikes over 4 square kilometers, trapped in the pre-existing fracture system of the sandstone host. Let's say 10% of the rare earth element mass accumulated in an upper magma chamber roof zone in bastnasite minerals. We've now created ourselves a success case hypothesis, which justifies us going to collect data to narrow the uncertainty ranges on each of those parameters. And if through collecting data, we can see that all of those are true, then the conditions for rare earth element accumulation are met, and we can predict that somewhere on that strike-slip fault system is between 2 and 10 million tons of rare earth elements. So what we're trying to do here is trying to predict the future outcome of our model. Mineral exploration is a forecasting activity, it's a forward-looking activity, which means the geoscience outputs that we create need to be in forecasting metrics the way if we were trying to predict the weather, or if we're trying to predict which horse is going to win on Saturday. So that takes us now to the minerals. Take us through province and then district and then prospect scales of evaluation to look at geological chance factors and our uncertainty on them. Here's a very schematic exploration workflow for generative exploration. We want metals exploration, ideally, to be a sequential process through a range of scales. And this triangle shape is drawn to depict a broad multidiscipline foundation, which enables us to lead up through 10 scales of investigation to a very small geographic location where we're going to drill to test our success case hypothesis. In an ideal world, the company will start with a business strategy at the foundation and come to a decision gate. And if the company decides to continue, its second stage will be to go and build all the knowledge and databases in GIS. Another decision gate follows, and if the organization wants to continue, then start doing some province screening or jurisdiction scale screening. With another green flag to continue, the team builds the 4D evolution of the host lithosphere, and then stage 5, the mineral system, a fluid system, which then quite dramatically intruded into the host lithosphere. And we want to know where its pre-existing weaknesses were. We can then go to plate analysis. Some companies also do mineral potential mapping. And then we're at prospect scale, building an inventory of prospects to build a portfolio of the ones that are worth drilling. And then the apex of the triangle to go and drill to test our entire business logic. The bottom half of this pyramid, or triangle, should I say, the purpose is to do cheap, flexible, regional scale desktop work to identify risks, and then a prospect scale where it's more costly, our studies are more detailed, more focused. The purpose is to reduce the risks that were identified in that broad foundation. Who does this? Ideally, the bottom half of that triangle is done by either the generative departments of companies, geological surveys, the research community, who then hand over to the prospect scale exploration teams to go and test those hypotheses. If a company already has tenements, then this is also useful to QC their current licenses and just sense check whether they still want to be in that area and to put their prospects into regional scale context. I'll very quickly walk us through just a few of those stages. Stage 1, clarify the organization's strategy. What we do with this triangle-shaped exploration workflow is to start on the left-hand side of one row and progressively move towards the right, and hopefully don't see any red flags. So are we looking for the right commodity? Is it the right strategic and portfolio fit for our organization? Are we in the right country, etc., etc.? And we do this for all of the geological factors, also the above ground risks, and then a third time, looking at the strength of our information. Is it reliable and relevant enough for us to build these hypotheses and to go spending lots of money? We're looking for red flags, hopefully we don't see any, and then we get to the end of this row and we have a decision gate where the company's decision makers decide whether it's justified to continue this project in this country or province, etc. All of this needs to be done in GIS. Just a little comment here that we should be data mining as well. A lot of explorations usually happen in each metallogenic province. We want to make sure all of that is available to us and in our models so we can build our geological and also non-geological base maps. The third stage is province screening. And several times I've been asked, why would you investigate a commodity at the province or the basin scale? And the answer is that mineral deposits are not formed by deposit scale processes, they're formed by tectonic scale processes. And so every drilling target should be put in its regional 4D context before spending lots of money on it, going into land access and all of the issues that enable us to be able to go drilling. Groves and Santosh, again, 2015, stated that poor global to province scale decisions are the reasons that many projects don't reach the feasibility stage. We need to be doing a lot more at the province scale. Groves and Santosh also said that 95% of exploration budget is spent at prospect scale, not very much at the larger than prospect scale. Maybe that's why we've got only a 1 in 1,000 chance of success with our prospects. So what we want to do, we've decided which countries we want to go into and a few regions or provinces that we now want to evaluate within those countries. We want to get as much data together, and if it's a data-rich or mature exploration area, we can be quantitative with our province scale analysis. We can build creaming curves like on the left. We can build discovery distribution size plots like on the right-hand side. Except that if there's this much data, we're already too late. The big discoveries have probably been made. What we want to do is to enter provinces which are underexplored and usually therefore have low data. And how do we screen those? So this is a whole presentation in itself that I won't do today. But what we want to be able to try to do is look at each metallogenic province and be able to get a qualitative assessment of how favorable it is for our organization's strategy. Again, those 3 map layers, the geoscience, the above ground risks, and third, and really important, how strong is our information? How valuable is it for our upcoming decisions? We use this to be able to determine which provinces and then properties to invest or divest in, what data to collect next at a regional scale to have a big impact. And if we deliver these kinds of outputs, it means that non-geoscientists can understand traffic light coloured maps and therefore make decisions on whether to go forward without all the geological nomenclature that we have. I'm going to skip over building the host lithosphere. That's another hour in itself. But let's go now to stage 5, which is the mineral system. At province, and then we'll do district, and we'll do prospect scale components of it. So a mineral deposit is just one small part of a large and predictable mineral system. Being predictable helps us to go and find it. A mineral deposit is just one focal point of many, where a series of essential ingredients all overlapped in time and space. Energy and mass was focused from a large to a small volume of rock. And so what we can do is look at the province scale questions about the mineral system framework, and then the camp or district or place scale, and then the prospect scale. What we're trying to do here is map the framework of a convective fluid system in geological history. So we want to map geodynamics and tectonics, and then put the smaller scale data sets, petrology, geochemistry, isotopes, etc. onto that framework. And the mineral system is very useful because it's got a larger footprint than individual prospects. And so we can use it to go exploring undercover and in greenfield terrains. And we can compare data rich with data poor regions with a mineral system approach. I've done this for rare earth elements, and I'll just go through that just for the next 5 minutes or so. First of all, rare earth elements. I'm not going to say much about them, other than that we hear a lot of press about them because of the rise in demand for clean energy and clean transport and also digital technology. And these metals are crucial for all 3 of those. The European Commission, the USA, Canada have all deemed rare earth elements to be critical raw materials. They're of high economic importance for our technological progress, but there's a high supply risk. There are very few suppliers around. So what does a mineral system for rare earth elements look like? And a mineral system I use as a noun. There are many of them. They can be compared with each other and even stacked on top of each other. So any province's mineral system is all of the genetically related resources, deposits, reserves, occurrences within a commodity that came from one specific provenance, one source region. It's the 4D extent from, in this case, the mantle, to all the known commodity occurrences that are related to it. So here in section view is a schematic example. You can imagine rare earth elements, one batch of them coming out of the mantle, 100 kilometers deep. Some of that commodity was caught in a magmatic facies in various different clay types. Some ended up going into metamorphic facies. Some progressed along the rare earth element global cycle into plays in the weathering facies. Some get washed down the mountain and down into the basin, where there are another set of different plays and prospect types. So I'm just trying to emphasize here that a play, a genetically related family of mineral deposits, should be our smallest unit of exploration, because it's a bit like a branch on a tree. We've found some apples. We know that there'll be some other apples still to find. It makes us think in a portfolio mindset. So how does one identify a mineral system and the genetic links between its mineralizations and its provenance? The first thing that we have to do is to prove that the mineral system exists, and that's just one mineralization above regional baseline concentrations. That can be a historic mine or just mineralization in drill core, for example. And that's why it's crucial that we do a lot of data mining, all that publicly available information, all the exploration companies that have explored and left the region. We want to put all that into GIS before we start spending our organization's money. If we find two mineralizations, we want to test that they are genetically related, which is why we use petrology, isotopes, geochronology, etc. We then, if they're related, want to link them on maps to their structural framework, which is why shallow geophysics and structural geology are always crucial at an early stage of exploration. We then want to formalize the relationships between the mineralizations and where they came from, their source. We want to map the geographic extent of the source region and possibly the further extent that hasn't been discovered yet, which is why we always need to be able to characterize at least the rare earth elements and other commodities, their source region and the yield potential of that source. How much commodity could have come out from it? How much is there left to find? We then want to link the mineralizations at surface with where they came from, in this case the mantle, via these translithospheric 100-kilometer tall structures, which is why we need to integrate geology with structural geology with tectonics and deep geophysics. They're crucial for understanding a mineral system. And once we've done that, we then have the foundation to go and explore for the undiscovered branches and undiscovered value in that same mineral system, maybe undercover. So that's good. There are lots and lots of inputs that would go into a mineral system framework. What we want to try and do is just distill all those many map layers that we could create into just a few essential ingredients at province scale. And the essence here is that if we can distill all of the work that we would do to just 4 essential ingredients, we can check that they've all coincided in time and space. And if one of those ingredients didn't happen, or if they happened in the wrong order, then there is 0 chance of mineral deposit. We don't need to spend any more money in this province. Let's move on. For rare earth elements at province scale, the 4 essential ingredients seem to be that the mantle was metaso-enriched in the commodity. There was also low-degree partial melting of the mantle to yield an alkali magma with not too much dilution of the commodity. There had to have been these translithospheric conduits, 100-kilometer tall fault systems, and then a momentary geodynamic event which enabled the magma to move and also created the temporary permeability up through the entire crust. That's very good. We've got to a Venn diagram with 4 essential ingredients, but how do we actually use that to go and explore and hopefully add value to our organization? What we want to be able to do is to convert mineral system science on the left-hand side inside that red box to targeting science. We want to be able to link geological and ore geology research and studies to the business of exploration and making a profit. We want to translate geological processes that create mineral deposits into a targeting system that we can put on maps. And I believe this is where research, industry, and policymakers should all be working more closely together. And actually, Australia is a really good example of where that works successfully. There are 4 stages to build a practical targeting system from Cam McCaig et al. 2010. Those essential ingredients, we try and work out what they are first of all. Then we want to discern what are the constituent components of this system. What are the processes that caused those essential ingredients? We want to then translate that into targeting elements, geological features that will be present if those processes happened. What would we go looking for if we were like detectives? And then turn that into targeting criteria. How would these features look on geological survey databases, free public domain data, for example? So here's an example of just one of those essential ingredients for the rare earth elements at province scale that's been turned from a mineral system component to a targeting system component. On the left-hand side, We start with low degree partial melting of the mantle. What would that look like in a geological survey database? We can use direct targeting criteria. If you find alkali rocks like foydites, melatites, kimberlites, you can be probably sure that there's been only low degree partial melting, and you can be confident between 0 and 1 in your uncertainty values. You can also go and look on seismic reflection data to see if you can see an updomed moho, or for example, regional scale elevated gravity data. But because that's indirect, our confidence range will be narrow. Our confidence range, correct, will be narrower, only between, say, a 0.7 or a 0.3 if we want to quantify it. We then determine what is the success case parameter, what does success look like, what does failure look like, and then who is the principal investigator in our team who understands enough about this to map it and explain it to the non-geological community. I'm going to go through a quick example of that, just a few minutes left. Here's an example of a rare earth element province in southwest Germany. You can see it on the map there, and a little bit of France. And we converted the essential ingredients to targeting criteria, and then we put them onto maps and stacked them on top of each other. We've coloured them in by how favourable our understanding is at province scale. We would call that risking at prospect scale when we can quantify it. And then we stack them on top of each other to see what's the weakest link in our success case model. So first of all, how rich is the mantle? Can it yield millions of tons of rare earth elements in the Rhine-Graben region of Germany? And that study hadn't been done, and there wasn't really enough information even to do a back of the envelope calculation either. So we just colour the whole area in yellow, neutral, null data, no hypothesis, don't know, but no reason to be negative. We then had to look for evidence of low degree partial melting, and we found alkali igneous rocks at surface, melatites, carbonatites. We were confident that holding a carbonatite, it is a carbonatite. So we were favourable. We can say that our hypothesis is favourable. Translithospheric conduits. During the Variscan orogeny, there were several cratered terrains, and you could see those northeast, southwest striking suture zones between microcontinents. And you can also see a Y-shaped strike slip system, which was permeable around 15 million years ago, and some of those alkali magmas came up them. So we have the conduits, and then a geodynamic event. Did one happen to get rare earth elements up to surface? We looked at all of the old oil and gas exploration seismic data. Why not? It's still geological data. And what we saw in this green area is that there was evidence of dextral transpression of the Rhine-Graben around 15 million years ago. And then in the rest of the area that's not coloured in green, there was no evidence of dextral transpression. So it shows us there was a plate tectonic scale event which reorganized the regional stress field, enabled permeability and magmas to rise to the surface. We stacked them all on top of each other. That's that major map in the middle. And then we said, what's the weakest link here? Sorry, we said, where do all four of these coincide in space and time? And what's the weakest link in our hypothesis? The diagram on the right-hand side shows they're the three areas where we found alkali magmas at surface. And we can postulate that maybe we could look at the strike slip system between three of those districts for maybe more evidence of that the mineral system has worked. The weakest link, as I said, was the richness of the source and the source yield potential. We just didn't have any way of calculating it at that time in the rush that we were doing this project. So if the organization still wants to continue with this project, and why not? You've got three districts there to go exploring in. Let's now go to the play or the district scale. What are the four essential ingredients of the system at this scale? Different questions, different geological processes, different scale, different data sets to answer those questions. And it seems that, at least for the rare earth elements coming out of the mantle, the four essential ingredients, many ingredients distilled to the four categories. There has to be focused ascent of the magma rather than dispersed. We want the commodity to stay in a large mass. There has to be fractionation of the magmatic vehicle that's carrying it towards the surface, and placement of the commodity in a reservoir, in this case a magma chamber, and then commodity concentration. The rare earth elements either settle in layered igneous sequences or up in the roof zone of the magma chamber. And if you can map where all four of these may coincide in time and space, that would be the exploration license block to then go and lease. And you can see here with the asterisk that tectonic influences are really important, and this should be the spine, I think, to any mineral system framework. If the organization still wants to continue, now down to prospect scale within one of those districts, again, what are the four essential ingredients that can create a deposit at this scale? I think the host fracture system is one of the four. That is the reservoir into which veins or magmatic dikes exploit. The commodity has to be deposited, trapped, and then has to survive high temperature hydrothermal processes and low temperature weathering and alteration and erosion processes as well. And if you can map a geographic area where all four seem to coincide and to have occurred in the right order, that would be the place to drill to test your entire success case model back down to the business strategy. And again, structural geology, really important in the mineral system, numbers 9 and 10, fracture systems and transient permeability of them. So we've been through the mineral system. We found 12 essential ingredients from all the different layers that we want to put into a map. That's important because we saw from the dice game, the more chance factors, the lower the chance of success. So we have that method now to find or predict where could all the chance factors have overlapped. One of the initial questions I said at the start was, why do you collect geological data if it doesn't change a project's risk or value? What we're trying to do with data is to increase our confidence. Those coloured maps were confidence maps that I showed you. We want to increase our confidence that we understand those geological processes. If we don't know very much, we'll just give it 0.5, 50-50, maybe, maybe not. 0.5 multiplied by itself 4 times means that the team only has a 6% confidence in its own success case model, which doesn't justify drilling. So that's why we collect data, to increase or elevate our confidence and reduce our uncertainty ranges in the essential ingredients. We're doing all of this because we're trying to ultimately give a better decision ability to our executive management and our investors. We've been through province scale qualitative screening, to prospect scale probabilistic risking, to, as you can see in number 10 on the diagram there, give our decision makers informed portfolio decisions in the metrics that they understand for predicting a future outcome. So take home messages, just 1 minute left. We should all, as standard practice, be sequentially predicting what happened in nature from province scale down to prospect scale. Here's a method to predict and compare the chance of success of countries, provinces, districts, and then plays, and then finally prospects. We don't start at prospect scale. We're trying to identify the optimal property for our organization's exploration failure tolerance. The exploration business is a game of risk played for high stakes. Here is a very schematic diagram of a systematic recipe to enhance decision quality, all the way from building provinces to deciding where within a few square meters to drill. This is a success case logic. It's globally applicable. It's been proven for decades for other commodities. It helps to improve decision quality, and it's applicable, I think, to a range of metals. I want to emphasize the base unit of exploration should be a play rather than a prospect, because that instills a risked portfolio mindset into all of us as we work every day. Here is the mineral system and its larger context for rare earth elements, and I think that this can be simply adapted to help map for nickel, zinc, copper, gold, lithium, graphite in a portfolio mindset. There are the essential ingredients at 3 different scales for the rare earth element mineral system to build a prospect portfolio. We identify essential ingredients, we translate it into a targeting system, we build and map our confidence in our success case model, and then we only spend money acquiring data that reduces our uncertainty in the success case inputs. This all seems quite tedious, but if it's done with your own organization's data and public domain data, it's much cheaper than drilling in the wrong place once. We quantify and then map our confidence in our success case geological models. Here you can see 4 essential ingredients on the left-hand side, stacked on top of each other to create a composite common risk segment map on the right-hand side. We overlay that onto the exploration license area to decide whether we want to invest or divest in particular properties, to be able to compare other properties, maybe form joint venture with partners, or acquire junior exploration companies, etc. Which information should we collect? The one that can change a red to a green, if that's possible. And using maps like this mean that non-geoscientists understand all of our work and our outputs. The best exploration decisions happen when the decision makers have all the relevant information, not just costs, not just grade or tonnage estimates, but expected value of the portfolio, value of information, geological uncertainties, chance of success, and the risks. A few thank yous. Jessica, GeoHug, and all of you for participating. Thanks very much. Southern Geoscience for recognizing this approach and how it helps build efficient data surveys for clients. Thanks to Julianne Sharples, Jonas, and David for artwork and map work in earlier versions of this PowerPoint. Geological are going to host in September a 2-day professional training course, expanding on what I've talked about here. So thank you to them for recognizing that vision. And to High-Tech Altcarb Horizon 2020 Consortium for all their wisdom on rare earth elements. So if you'd like to talk more about this, put your prospects into a probability of success mindset, feel free to reach out. It'd be great to speak to you, and it'd be great to discuss this with you all just now.